Dear students, today a short movie about integration, and I'm gonna try to give a intuitively explanation of what integration actually is. So let's take a bucket with a 50 liter bucket with a scale on the side, and on the left top we have a hose with water with a valve. And if we open the valve, we can have the water go from 0 liters per second till 3 liters per second. And the dial in the top will also show it. Well, let's see what happens when we first try to open it for 1 liter per second and then for 3 liters per second. So we open it to 1 liter and we see the water rising in the bucket. And if I open it even further, then we see the water rising more quickly. And if I stop it, then the water stays the same, the water level. Well, basically what integration is, if we integrate the flow of the water into the bucket, we will get the height of the water level in the bucket. And that's basically integration. So maybe it's a little bit clearer if I make a graph. Again, the same situation. We're gonna go to 1 liter. The blue in the graph is the input line, and the orange is the resulting water height. So when we're talking about integration, basically, if we integrate the blue line, we will get the orange line. So basically, it's filling up a bucket. So it accumulates the input. It accumulates the input, and that's the outcome of the integral or the integration. So when we look at the way we write this down mathematically, and I'm gonna name the input I, and so the amount of water coming into the bucket is gonna be I. That's amount certain liters per second. And the height of the water level I'm gonna name U. And we're gonna do the integral over time. That's not always the case. We could also do across distance, for instance. Then it would be something like dx. But now we do it over time, and that means that the dt indicates we're integrating over time. Well, this is one way of writing down the integral. This is a bit more common. And what we now also indicate is the boundaries of the integral. Now we're really talking about a certain integral. And what you see here is the starting time, basically. So we start adding, accumulating things from time 0, and we will continue it until a certain time. And the resulting outcome of this integral is this height. And I'm actually also skipping a little bit here, so I'm going to add a little bit. What we assumed just now was that we started with an empty bucket. If we don't start with the empty bucket, we need the water level at t is 0, and so then we would get this formula. Okay, so it's actually kind of easy. Let's take it at another thing, and maybe it also will ring a bell a little bit more with regard to the math you got in school. So again, we have a bucket, but this time we're gonna slowly increase this flow, and we're gonna do it linearly with time. So that means it's gonna be slowly getting more flow. And that is also indicated by the blue line. The blue line is slowly in a linear fashion, so it's a straight line. You will see it increasing. The interesting thing is that the orange line, and it's actually logic, you will see that the bucket, when the flow is more, the bucket fills up quicker. So the orange line, what we see here now, is that the orange line goes actually, it's not straight at all. Well, this case, we have chosen the input such that we can do it with an analytical description. So the input flow is 3 divided by 20 times the time. Well, let's see. That means that if it's 20 and t is 20, then we would have an input flow of around 3 liters per second. Well, it seems about right. And if we want to know what the water level height is, again we have our formula. And this thing here, we gonna take the integral of a certain thing with t, etc. This thing we can actually calculate mathematically, and then you will get this kind of a result. This trick, there's a lot of math tricks involved in going from here to here. There's a lot of videos on that on YouTube, so I will skip it for now. But well, this is what we normally see. Well, you have to do integration and primitive, etc. All that calculations, and this is all nice, but it only works if you've got a relatively simple function here, formula here. If this is a little bit more complicated, then this step becomes extremely difficult or impossible. And that's a little bit a bridge to the next situation. Here we got input flow, which is random, sort of. It fluctuates. And now we cannot use math anymore, at least not the math we were taught in school, to describe the orange function. So to describe the water level. But we would still like to do that. We would like to say something about the water level in the bucket. So this thing, well, actually, IT, the function for the flow, it's kind of random. It's going to be difficult. And what you still can do is approximate it by computer, using a computer. And then we replace this integral with a sum. This means a summation. And basically, yeah, you do see kind of something similar. Well, the first thing, the computer does it in steps, in small steps. So it calculates something and then it calculates the next time step, and then the next and the next. So that is, here you've got the dt when you're a not math genius, but when you're a little bit experienced, you know that the dt is actually some kind of limit going to 0. Here it's just a real number, but a very small one. And what it does, the computer, it just adds the flow at different points in time times the elapsed time. Well, but that's actually what the bucket does, right? So it's kind of mimicking the bucket. And this thing, it doesn't matter how this function looks. This can be a really complicated function, can even be random. It doesn't matter, you can always calculate this. So the computer can always predict this orange line, exactly like the bucket did. Well, what you see already, that now we've got not a height at a certain time, but at a certain step. So what is the relation between that step and the real value? So firstly, it's an approximation. So it's not totally equal, it's almost equal. And that depends a lot on how small this delta t is. If it's really small, then this approximation actually pretty accurate. So if, for instance, the time step is 1/100 of a second, and we would like to know, for instance, what u100 is, and the time step is 100 of seconds, well, we can use this formula, and you will see that u, the 100th calculation of the u, will give the real u at t is 1 second, because 100 times 1/100th is exactly 1 second. So this is the relation between our discrete points and the real value. And this approximation is pretty good as long as this one is small. Okay, so that's pretty cool. What we did not yet discuss, all this time we've been talking about adding the water, etc. But of course we could also have that the water is removed, and still we then talk about an integral. So what we've got now, I've got a tube, and the tube can either go the water in or it can go out. And with the arrow and also with the dial, I'll indicate what's happening. So now the water is going in, the water rises in the bucket. But if we start sucking the water out, so now the water is removed, then the level goes down. Is this a different case than all the cases we talked about before? Well, not really. The only thing is now the input can also go negative. And it's still the same story. So basically it just accumulates all the values it receives, and that's the outcome of the integral. But if the values are negative, then the outcome of the integral goes down. Okay, no problem. So that's the last model I wanted to show you. I wanted to thank Anton for the idea of this movie, and I hope you will get a feeling about what is really an integral. Good luck!